Okay, so welcome everyone to this week's Geometry and Topology seminar at Durham. So it's a pleasure to welcome Jaime Santos Rodríguez. He's at the Universidad Autónoma de Madrid in Spain, and he will later join the Max Planck Institute in Bonn. And he will talk about Wasserstein isometries of closed Riemannian manifolds. So welcome, Jaime.
Thank you very much. First of all, I would like to thank Fernando for inviting me to give this talk. It was supposed to be scheduled on July, I think, but things happened.
Right, the pandemic.
So today I'm going to talk, as Fernando just mentioned, on Wasserstein isometries. And this is part of my PhD thesis. I worked on many things, and well, this is the last chapter. And well, let me begin. Using optimal transport, it is possible to define a distance between probability measures. This distance is called the Wasserstein distance. And with this, we can give the space of probability measures a metric, the Wasserstein metric, and this metric will reflect many geometrical properties of the base space M. And well, the talk is divided into two parts. In the first one, I will talk about what the optimal transport is and some properties of Wasserstein spaces. And in the second part, I will actually talk about the isometries of Wasserstein spaces and the results we obtained. So for the first part, consider the following setting. We have a pile of sand, say mu. It is modeled by a probability measure. And we have, say, some hole nu, which is also modeled by a probability measure. And we want to send all the mass in mu to nu. And to do this, well, you pick up point x at the support of mu, and you send the mass at that point to another point y. You repeat this for every point in the support of the initial measure, and you end up with a way to send all of the sand from one pile to the other. One could also do something like this. Say we have too much mass at one point, like this x here, and we can split it. Maybe send a little bit to y and the rest to z. And again, we repeat this for every point in the support. This gives us a plan to send mass from one location to another, and this is modeled by a probability measure, but now in the product space. Say this happens in a manifold, then we would have a probability measure in m times m. And we would like to find the best possible way to send the mass. And the best possible way in the sense that, for example, it minimizes the distance. More rigorously, we have the following, the so-called Monge-Kantorovich optimal transport problem. We take two probability measures, mu and nu, some exponent, p, which is in this interval, and we're looking for to minimize this functional that sends a measure pi and computes the integral of the power p of the distance. And we're taking this measure pi in the set of admissible plans, which are measures in the product space, such that they have the appropriate marginals, meaning that when I evaluate at sets of the form A times M, I recover the initial measure mu. And when I evaluate at sets of the form M times B, I recover the final measure. This problem has nice things. For example, the set of admissible plans is never empty. I always have at least the product measure between them. And solutions always exist. Solution exists because this functional is actually linear, and the set of admissible plans is compact with respect to the narrow topology. So we can always minimize this. And the solutions are called optimal transports and are denoted like this. We could also ask for more. For example, consider a measurable map T from M to M, and recall that the push forward measure is defined like this. The push forward of mu by T at a set A is simply computing the measure of the inverse image of A. And with this, we could consider, for example, for two probability measures, mu and nu, we will look at maps that push the measure mu to nu and take this integral instead. Notice that this plan is actually admissible in the previous sense and is equal to this. And this formulation of the optimal transport problem is the original one given by Monge. And we are looking now to minimize with respect to all maps that push forward the measure mu to nu. That is, we are not splitting mass in this case. So it is much more restrictive. This problem has some difficulties. For example, if the initial measure is, say, a Dirac delta, and the final measure is not, then there are simply no maps. And even if there are maps, this condition is not sequentially closed. So we can't find the minimizer with this constraint, at least in some cases. Later, I will describe what can we assume from the initial measure in order to solve this. And well, using the optimal transport, we can define a metric. Consider MD a Riemannian manifold. D will be the Riemannian distance. And we will not consider every probability measure for some exponent P. We will only look at probability measures with finite P moments. And for these measures, we can define the L2 Wasserstein distance simply by taking the solutions to the Monge-Kantorovich problem. And this distance defined in this way is called the L2 Wasserstein distance. We need this condition on the moments, because otherwise these might not be finite. So we need this. Now, some properties of the Wasserstein space. Well, the Wasserstein space is compact if and only if the manifold is compact. We can define a map that sends points x to Dirac deltas. And this is an isometric embedding of the manifold into the Wasserstein space. That is, we have an isometric copy of the Riemannian manifold inside the Wasserstein space. But the Wasserstein space is clearly much larger than the manifold. For example, for every natural number, we can pick different points, take a convex combination of them, and get different probability measures. And well, finally, some geometric property. If my manifold has non-negative sectional curvature, then the Wasserstein space for the exponent p equals 2 is also non-negatively curved in the sense of Alexandrov. That means taking comparison triangles. Another very important property that I will need is that the Wasserstein space is a geodesic space. By geodesic, I will be talking about curves gamma from 0, 1 into the space, such that they have constant speed. That is that the distance between gamma s and gamma t is just the absolute value between s and t, and multiplied by the distance of the endpoints. I will denote the space of geodesics by G of M. And the nice thing about the Wasserstein space is that I will also have geodesics in there. And well, I will need to define some things. For every t in 0, 1, I have evaluation maps, E of t, which simply take a geodesic gamma and evaluate it at time t. And we have this result by Ambrosio and Gigli, that if we have a Riemannian manifold, then the Wasserstein space is geodesic, and we also have a characterization of the geodesics. Being a geodesic is equivalent to existing, so that there exists a measure, eta, now supported on probability measure, on geodesics of the space, such that by pushing forward with the endpoints, I recover an optimal transport, and that also by pushing forward now with the evaluation maps, I recover the geodesic. So this means that the optimal transport, this movement of mass from one location to another, the points in the support move along geodesics. And this measure eta contains the information on which geodesics I'm using and how much mass I'm sending from one point to another. Let me give a couple of examples of how geodesics in the Wasserstein space look. At least some simple ones. Take 2 points, P and Q on the manifold. It is easy to see that there's only one admissible plan, the product measure. Now the geodesics on the Wasserstein space can look, for example, like this. I can take mu of t to be, so Dirac deltas supported at a geodesic between P and Q. So I'm moving the mass along Dirac deltas. But I could also do the following. Say, for example, we're in S1, and that P and Q are antipodal. There's more than one geodesic between them, say gamma up here and sigma down here. And we can choose to split the mass along these geodesics. Say, for example, at time t, I take half the mass from P up here at gamma of t, and the rest at sigma. And I move the mass along this curve. this curve that consists of measures that are supported on 2 points. So I will have geodesics that look very much like those of the base space, but I could also obtain geodesics like this one. And I could also divide the mass in other ways. I could, this is just an example of a half and half, but I could split it differently. If we ask more of the initial measure, for example, if the starting measure is absolutely continuous, then the optimal transport will be unique. It will be given by a map. That is, it will solve the Monge's problem. And the Wasserstein geodesic, starting from mu0, will be unique. And the nice thing is that for every intermediate measure, the mu of t will still be absolutely continuous without any information on the final measure. We just need to know that it starts from an absolutely continuous measure. I will mention something else when I will talk about the results, but the idea is that when we are moving this mass, it doesn't just disappear midway. If something has positive mass, it just sort of stays like that. Okay, and now on to the main problem, isometries of these spaces. Let's consider the following. Let is of M be the isometric group of M. I can define an action in this way. For any isometry G and every measure mu, I send it to the push forward by this map G. This will define an isometric action. And now a very natural question, at least to me, is, okay, given that the manifold and the Wasserstein space have share many geometrical properties, do isometries from the manifold make all of the isometries of the space, or is there any way in which the Wasserstein space can be more symmetric? That means this, whether the isometric group of M is exactly the same as the isometric group of the Wasserstein space. Well, this question has been already addressed in the Euclidean case by Kleckner, and surprisingly, he finds isometries in the L2 Wasserstein space of the Euclidean space with P equals 2 that don't come from isometries of Rm. And I would like to describe these isometries, and so later this gives a motivation for the problem I'm actually addressing. Let me observe two things. If I have an isometry, or really any map, the push forward of a Dirac delta is again always a Dirac delta. This also happens if I take convex combinations of measures. It will act linearly in a way. It will preserve the atoms. And second, if mu is a probability measure in Rn, then it has a unique center of mass, a unique barycenter. That is dysfunctional, that sends a point in Rn to the integral of the square of the distance from x with respect to the measure mu, has a unique minimizer, which is known as the barycenter, center of mass, or facial mean. Well, I will describe the exotic isometries just in the case of the line, which is the simplest. First, we have this lemma for n greater or equal to 2. This set delta n are the totally atomic measures, mu, which are convex combinations of points in R that are endpoints. And the result is that the convex hull of this set is the next set. Now the total atomic measures supported on n+1. Let me give an example. For n equals 2. Take 3 points in R, arranged in this way, x1 less than x2 less than x3, and take some probability measure mu. Then it can be seen that this measure mu is in the interior of a Wasserstein geodesic, of the Wasserstein geodesic joining these two measures, which are simply take the mass that was at x2 and put it on x1. So this has more mass. And the final measure is just, okay, this lambda2, put it here. So clearly the Wasserstein geodesic would do the following. It will take this mass lambda2 from x1 all the way to x3, and by the condition it will pass at some point, at this point x2. So at some point in the interior of the Wasserstein geodesic, I will pass this measure. So why do I need to consider this? Well, because with this, it is enough to define the isometry or in the probability, in the Wasserstein space of the line, just in delta 2. Because if I have it in delta 2, I can define it in delta 3 and so on. And notice that we also have that the Dirac delta, the measures at delta 2 can be written in terms of 3 parameters, x, sigma, and p, which take this form. The number p will hold the information on how much mass is given to each atom. X is the barycenter of the measure, which always exists and is unique. And sigma will be the distance between the barycenter and the measure. And well, these are just the atoms, which are written in terms of these quantities. So with this expression of the measure, I can define a map in this way. Pick some t, a real number. And I define a map from delta 2 to delta 2 simply by taking a measure, mu, with parameters x, sigma, and p, to another element of delta 2, but now with parameters x, sigma, and p plus t. That is, I'm changing the mass given to each of the atoms. Also notice that if I have a Dirac delta, it will fix it. The barycenter of a Dirac delta is itself. And we also have this behavior that that I drew here. Say we have X, the barycenter, and I have in blue here this measure mu. I apply the map, and what happens is that one of the atoms, say for T positive, will get closer to the barycenter, and the other will be farther away. And if we keep iterating this map, we will see that these measures, P plus T, will have one of the atoms getting closer to the barycenter and the other mass going to infinity, to minus infinity in this case. And seeing this behavior, we thought, okay, maybe we can ask for our manifold to be compact, so that there's no way that the mass can go to infinity, and perhaps we can then prove that there are no exotic isometries. That is, that we can try proving that, okay, maybe in this case, under compactness, the isometry groups of the manifold and of the Wasserstein space are the same. And we obtained some results assuming something on the manifolds. I will describe it later. But first, we need some information of how the isometries behave on the Wasserstein space. So I talked at the beginning about the Monge problem, which was finding maps T that solve the optimal transport. And it turns out that the original problem posed in 1780 was solved until 1991 by Riemannian, by assuming that the starting measure is absolutely continuous. This was later extended by Robert McCann in 1995 for Riemannian manifolds, and this for the exponent p equals 2. And for general exponents, p in this range, and actually this result holds for more general spaces other than Riemannian manifolds. Let's just leave it at Riemannian manifolds. And we have these nice properties that the geodesic that starts from an absolutely continuous measure will always be unique. And the intermediate measures of the geodesics will still be absolutely continuous. Okay, so with this result, I can actually say something about how the isometries of the Wasserstein space behave, at least in some cases. Take an isometry phi, a starting measure mu, and consider the following. We have mu, the image of mu under the inverse of phi, and we take the geodesic. Any intermediate measure, nu, will still be absolutely continuous. And so, since phi is an isometry, it sends geodesics to geodesics. And now we have this on the right. We have that nu goes to phi of nu. Now this is mu, and this forces phi of nu to be absolutely continuous. So we have that there exist measures, absolutely continuous measures, that remain absolutely continuous under Wasserstein isometries. And we also, this will be very useful later. And we also have this nice result about a functional. Take a exponent p, some starting measure mu, absolutely continuous, and then the functional, that is the Wasserstein distance from mu to the power p, is strictly convex. Strictly convex in this sense, that if I take a convex combination of two measures, the distance will be strictly less than the combination of the corresponding distances. For Euclidean spaces and p equals 2, this was proved by Sant'Ambrogio. The proof is exactly the same. It really just depends on the measure mu being absolutely continuous and the fact that the transports are always given by maps. So we took the exact same proof and it holds in this setting. And well, now for the first result, we obtain, if you have two closed Riemannian manifolds such that for some p between 1 and infinity, the Wasserstein spaces are isometric, then the manifolds themselves are also isometric. And I would like to give a sketch of the proof. Consider the isometric phi, and we have this situation in this diagram. We have that both manifolds can be isometrically embedded in the corresponding Wasserstein spaces. They are the Dirac deltas in the Wasserstein space. So we would like to show that the restriction of the measure of the isometric phi to these isometric copies sends Dirac deltas to Dirac deltas. So we can define an isometry now at the level of the Riemannian manifolds. And the idea is like this. Take some absolutely continuous measure nu, such that its image remains absolutely continuous under phi. I have already showed that these measures exist. And then I notice some things. First, the functionals that are the p power of the distance from nu and from phi of nu are strictly convex. Since they are strictly convex and the space is compact, then the maximum is achieved only by Dirac deltas. And finally, it is clear that if I send the argmax of this functional under phi, I obtain the argmax of the other functional. So this means that there's some Dirac delta here that is sent under phi to another Dirac delta. There's at least one. And this is all I need. Because of the following. Say the point that does this is x. So phi of delta of x is again a Dirac delta. So since we're in a Riemannian manifold, we'll know that for almost every point p, if I look at the geodesic from p to x, I can extend it a little bit to another point q. So in the Wasserstein space, I would have something like this. geodesic given by Dirac deltas that passes through delta of x at some point. I apply phi. So now I have a geodesic from phi of delta p to phi of delta q that at some point is a Dirac delta, delta y. And now I use a result of Ambrosian-Gigli that says that if I have a Wasserstein geodesic, then for all intermediate measures, in this case, phi of delta of x, there will be a map, T, that pushes forward this intermediate measure to the final measure, and the plan is optimal. What does this mean? Well, since push forwards of Dirac deltas are always Dirac deltas, and we have an intermediate Dirac delta, this forces the endpoints of the Wasserstein geodesic to also be Dirac deltas, because this proposition tells me that there will be a map, an optimal map that sends this measure to say this measure, and another that sends delta y to this. So this means that the isometry phi sends delta of p to another Dirac delta. Since this happens in a dense set, I'm done. And with this, I can define a map, f from n to n, that simply takes a phi of delta of x to f of x. And since it's an isometry at the Wasserstein space, we have this equality here. Since I had an isometric embedding of the manifold M, this distance equals the distance in M. And same thing happens for the manifold N. So we obtain an isometry between M and N. And I'm done. Okay, but what about the original question? What about finding whether or not the isometry groups of the Wasserstein space coincide? Well, we have obtained it for some spaces. I will mention them at the end. But let me describe, at least in the simplest case, that of the sphere, the result. That is that for the sphere Sn with its standard metric, the isometry groups of the sphere and of the Wasserstein space of the sphere coincide. And well, from the previous result, I already know that Wasserstein geodesics send Dirac deltas to Dirac deltas. So I can restrict myself to isometries that fix all Dirac deltas. So I will only need to prove that if an isometry fixes all Dirac deltas, then phi must be the identity. If I have this, then the result follows. Okay, let me describe the proof. Given a point P in the sphere, there exists a unique point Q at maximum distance. In this case, P and Q are joined by infinitely many minimizing geodesics. Well, if n is bigger than 2. And now I consider a measure supported on a parallel, like in the drawing here. And notice that for each point in the support of this measure mu, some x here, there exists a unique geodesic from P to Q that passes through that point. And it is easy to see that mu will be in the interior of some Wasserstein geodesic joining these 2 points. We could notice that for any point in the support of mu, the distance to P is exactly the same for any point here, and the same happens for the antipodal. So this already tells me some things about how measures can be in the interior of Dirac deltas. And I use this to obtain that since phi fixes both delta P and delta Q, BR1, then phi of mu will be in the interior of some geodesic. And what's more is that this phi mu will be supported in the same parallel as the original one. And the nice thing is that this sort of behavior happens for a larger class of measures. But let me explain first the plan. If I take the totally atomic measures, then the union of all of them is dense in the Wasserstein space. And that measures here are supported on, at most, m parallels, like in this drawing. If I take mu to be lambda 1 delta x1 plus lambda 2 delta x2 plus lambda 3 delta x3, I have a situation like this one. This measure in delta 3 can be at most in 3 parallels. And I obtain the following result: that if you start with a measure mu that is supported on some number of parallels m, like here in red, m written in this way, then under the Wasserstein isometry, the image will still be supported on the same parallels. The mass given to each parallel will be the same, with this part here. And the situation just looks like this. Like, imagine that this mu1 is taken to this mu1 tilde, the mu2 to mu2 tilde, and so. And so with this result, I will, in order to obtain that phi is the identity, I just need to prove that phi of mu is identity for measures in delta m. So take one of those measures here. Then for x1, I can consider the antipodal point. By the previous result, the image of phi under this, the image of mu under the isometry phi will take this expression. The original delta will be at the parallel of radius 0 with the same weight, and the other ones would look like this. Delta of x2 would be some measure m tilde of 2, and so. And I can repeat this for every atom. I could now consider, okay, from x2, I can take the antipodal. The situation looks like this. Then I will obtain then that phi of mu will be a1 delta xi x1 plus a2 delta x2 and the remaining. I repeat this for every atom, and I conclude that phi of mu must be the same mu, and that's it. By density, I obtain that phi must be the identity, and so the isometric groups of the Wasserstein space and of the original sphere are the same. Well, using similar ideas to the ones I presented just now, we can repeat this for every cross, every compact rank 1 symmetric space, and obtain the same thing, that the Wasserstein space, the isometric groups of the Wasserstein space and of the manifold are the same. And if we assume that M has strictly positive sectional curvature, and that the exponent is p equals 2, then we can also obtain the result. The idea is taking advantage of the fact that for p equals 2 and positive sectional curvature, we are again working with Alexandrov spaces. The proof is more involved, but it also relies on first proving that an adequate set of measures remains fixed. In this case, the set of measures supported at a geodesic, and then looking again at totally atomic measures and proving that each atom must be fixed. And well, this is all I wanted to talk about. Thank you for your attention.
Okay.